In previous lessons, we have learned how to code fixed-time signal controllers, priority rules, and stop signs. For a fixed-time signal control, we used vSim fixed-time controller. However, in most practical applications, there is a need for a more comprehensive controller to emulate real-world actuated traffic signal operations. In addition to the simple fixed-time control, vSim also provides a powerful ring barrier controller, RBC. RBC is capable of modeling complex real-world traffic signal timing, such as actuated control, railroad preemption, and transit signal priority. Let's start by exploring the RBC user interface. The RBC user interface can be accessed by setting up a new RBC signal controller using Signal Control, Edit Controllers, and choosing Ring Barrier Controller from the Type drop-down menu. Define a unique number to identify this new signal controller. You can optionally choose to name this controller. To initialize the RBC user interface and to start coding your signal timing plan, click on the Edit Signal Groups button. In the resulting RBC user interface, you will see a feature selection tree to the left. There are 4 main parent nodes in the selection tree: base timing, detectors, preamps, and transit priority. Each node encapsulates one or more child nodes. Typically, in most applications, base timing and detectors are sufficient, whereas preamps and transit priority are used in advanced scenarios. For convenience, only the selections made in this list will show up in the tables on the right. In this way, users can choose to display things that are relevant to their particular signal timing plan. Beneath the selection tree, you will see 2 separate boxes: pattern-specific properties and global values. Pattern properties are specific to the pattern, which can be selected by double-clicking the intended pattern in the selection tree. Global values are properties that are global to all the patterns in the signal timing plan. In addition, there are 2 frames at the bottom. The first one displays the signal timing plan of the pattern that is selected in the Properties window. Second frame displays the errors, warnings, and messages associated with the controller. These are updated as the timing is modified. The View menu item allows you to toggle the Tree View panel and the Message panel. For convenience, the interface also provides a way to store the list selections and graphical properties for later use. To save the settings, choose File, Settings, Save Settings, and name the file as RBC in the resulting dialog box. In addition, the settings can be loaded from a saved file using File, Settings, Load Settings. RBC will automatically load the rbc.ini that exists in the local working directory. However, setting file with any other name will need to be loaded manually by the user. In the base timing node, you will see 6 child nodes: timing by signal group, patterns and coordination, pattern schedule, sequence, conflict signal groups, and overlaps. In timing by signal group, you will see basic and advanced nodes. In this node, we define properties that are common to all patterns. Patterns can be thought of as time-of-day plans. It is important to note that coordination requires a pattern. A signal controller without a pattern is always free-running, although a pattern can also be run in free mode. RBC allows a maximum of 8 patterns per signal timing plan. A pattern inherits all the information and timing by SG, as well as using the information within the pattern. Any values set within pattern that are duplicates of variables within timing by SG override the timing by SG. 0 values within patterns are ignored. However, for those checkboxes that are duplicated, the pattern can only turn on checkboxes that are off in timing by SG. If they are on in timing by SG, they will be on when the pattern is running. We will talk more about patterns in the next lesson with coordinated signal timing. The pattern schedule table defines the start times of each pattern. By default, basic timing is free running and starts at 0. The sequence table defines the ring barrier diagram for the signal timing plan. RBC allows users to define up to a maximum of 4 rings and 8 barriers. In the detector node, you will see 2 child nodes, vehicle detectors and pedestrian detectors. These tables are used to identify or reference the detectors that are created within vSIM, and these tables do not actually create detectors in vSIM. Now that we are familiar with the user interface, let's start by defining a fully actuated free-running signal timing plan. For a simple free-running actuated intersection, we will need to define basic timing by signal groups and the associated detectors. Since our signal controller is free-running and does not change by time of day, we do not need to define a pattern. We will code an actuated control at the T-intersection in the middle of our network, where previously we coded a fixed-time signal controller. First, we will need to look at our signal timing plan to see what we are trying to model. In the signal timing plan, signal group 6 represents the northbound movement, signal group 4 represents westbound movement, and signal group 8 represents eastbound movement. Since this is a free-running intersection, there is no defined cycle length. The minimum green for the northbound approach is 5 seconds, and the maximum green is 20 seconds. The splits for the movements are also shown in the image. There are 2 barriers and 2 rings in this timing plan. Signal group 6 belongs to one barrier group, and signal groups 4 and 8 belong to the other barrier group. Let's start entering the data by adding signal groups. In timing by signal group, enable the basic node. Double-click in the first cell to define the first signal group, number 6. Then press the Tab key to enter the value and to switch to the next cell, and then define signal groups 4 and 8 as well. You can define a name for each of the signal groups if you wish, but this name is not used within vSIM. In the minimum green field, enter 5 seconds for all signal groups, 6, 4, and 8. Min green is the minimum green time served for the signal group when it is called. Next, enter 3 seconds for yellow clearance and 2 seconds for red clearance, all red, for all signal groups. In the vehicle extension field, enter 4 seconds for all the signal groups. In the Max 1 field, enter the maximum green for signal group 6 as 20 seconds, and signal groups 4 and 8 as 30 seconds. If you do not understand the terminology of certain terms, you can always use the Help menu to open the RBC manual to find its definition. Let's go ahead and open up the RBC manual and search for vehicle extension and Max 1 parameters. The definitions of various parameters are available under Definitions node in Content tab. Let's choose Vehicle Extension Definition from Base Timing and Basic Node. Similarly, we can read the Max 1 definition. It is always a good idea to read the definition of parameters. The pedestrian signal group is defined in the signal timing of its parent. Let's define pedestrian signal groups 106 and 108 under parent signal groups 6 and 8 respectively. Both pedestrian signal groups have a walk time of 5 seconds and flashing don't walk FDW time of 12 seconds. Let's mark 4 and 8 as the startup signal groups. These are the signal groups that are shown when the signal controller is first started. Also, we flag signal groups 4 and 8 for dual entry. The dual entry feature is often used for through movement signal groups, such that if one signal group is called when crossing the barrier the signal group in the opposite direction will automatically be started as well, even if it doesn't have a call. After defining the signal groups, we need to define the sequence of traffic movements at the intersection. To do this, first display the sequence table by selecting it in the node tree. In the table, you will see rows are identified as rings 1, 2, 3, and 4. In RBC, there are a maximum of 4 rings available for use. Let's define the sequence. First, define 6 in the first column of ring 2, and then define 4 and 8 in the second column of rings 1 and 2. Now, create a barrier between signal group 6 and signal groups 4 and 8 by double-clicking over the header bar. You will see that the cursor changes to a plus or minus symbol when you move it over the header bar. The barrier is always created on the right side of the column. To remove a barrier, double-click on the column to remove the barrier to the right. RBC automatically creates a barrier at the end of the table by default, so there is no need to define the last barrier in the timing plan. Next, select the pattern schedule. In the pattern schedule table, you will see that the RBC controller by default defined free as pattern number and start time as 0. As mentioned earlier, a signal timing plan without a pattern is always free running. The start time defines the start of the timing plan in simulation seconds. Since this is a free-running intersection and we want the controller to start at simulation second 0, no changes are necessary in this table. The final step in defining an actuated signal control is to define the detectors and associate them with signal groups. Let's display the vehicle and pedestrian detector tables by selecting them from the tree. In the resulting table, you will see several options for defining detectors. However, many of these parameters are for advanced applications. In our simple application, we only need to define the detector number and associate them with signal groups. First, let's define the detector numbers. For ease in understanding and coding, we will use the same numbers as the signal group numbers to identify the detectors. You can use any number to identify a detector, but you must use the same identifying numbers when defining the detectors in vSim so that the controller and vSim can communicate on the status of the detectors. For our example, we will define one detector for each approach. Detectors 6, 4, and 8 are defined on the first row. Next, we need to define which signal groups are called by each detector. Let's associate detector 6 with signal group 6 by selecting signal group 6 from the drop-down menu. It is possible to associate a detector to call more than one signal group by using Control key while selecting the signal group. Finally, call signal groups 4 and 8 using detectors 4 and 8 respectively. A detector call will only place the initial call to a signal group to make it turn green, but it will not extend the green time of the signal group beyond minimum green. To extend the signal group, you need to define what signal groups are extended by the detector. In the real world, there might be more than one detector for a signal group, one to call the signal group and another to extend the signal group. This example will use the same detector to both call and extend the signal group. Let's define each detector to extend its associated signal groups. First, select detector 6 to extend signal group 6. You can also choose to extend more than one signal group by selecting more than one signal group from the list using the Control key. Similarly, extend signal groups 4 and 8 using detectors 4 and 8. For our example, we will leave the other parameters at defaults. Next, let's define the pedestrian detectors. Pedestrian detectors are defined similar to vehicle detectors. Let's define pedestrian detector numbers 106 and 108, and then associate them with signal groups 106 and 108. If you need to add additional detectors in a signal timing plan, you can do so by clicking on the plus sign to the right of the detector table. RBC will automatically display 4 additional detectors per click. This is for display only. It does not add more detectors unless you also fill in the detector information. Finally, let's set the RBC frequency to 1. RBC frequency defines the number of times the controller will communicate with vSIM during simulation. Only one frequency can be defined per controller type per vSIM file. RBC allows the user to select a frequency from 1 to 10, however the simulation resolution must be such that such communication is possible. At this point, we have completed the entries for a simple free-running actuated signal timing plan. RBC also provides a graphical view of the timing plan, which can be displayed by selecting the toolbar at the bottom. You will see 2 different toolbars at the bottom of the interface. One displays the timing diagram, and the other displays the errors, warnings, and messages. After selecting the toolbar to display the graphical signal timing plan, you will see that the timing diagram does not fit the screen. This happens when the cycle length is not defined, or when the cycle length is smaller or longer than the default timing window size. You can resize the timing diagram to fit the screen at any time. Right-click on the diagram and choose the Resize to Fit Screen option. This will display the timing bar so that it fits within the window. The graphic shows the rings and signal group numbers and their calculated split. The graphical signal timing plan also offers you a way to change the timing by clicking and dragging the signal group. For example, you can click on signal group 6 and drag it to 20 seconds. As you can see, the max 1 time of the signal group you are dragging changes simultaneously. If you want to avoid accidentally dragging the timing plan, you can lock the diagram by checking the Lock Diagram box. RBC also provides a basic check of the signal timing plan and provides errors and warnings. It is important to address the errors and warnings to successfully define a signal timing plan. Display the errors, warnings, and messages by left-clicking on the last toolbar at the bottom of the RBC interface. As you can see, we do not have any errors or warnings. Therefore, let's go ahead and save this file by clicking OK. RBC will then prompt you to enter a file name and location to save the signal timing plan. Remember to store the RBC file in the same folder location as the INP file. Let's name this file as Free Running and select Save. This brings us back to the original dialog box where we created the new signal controller. You will see that the file name is visible in the Data File field. This confirms that the controller and the file have been associated with each other. Press OK in the dialog box to confirm the changes. Before proceeding any further, it is always a good idea to save the vSIM file. Click the Save icon on the toolbar to save the file. After saving the INP file, the next step is to place the signal heads and detectors at the intersection. Let's zoom into the middle of the network to get a better view of the T intersection. Since signal heads were covered in a previous lesson, we will skip ahead to a file in which the signal heads have already been added for this intersection. After defining the signal heads, we can start defining detectors. Since detectors are placed in relation to the signal heads, we can select the signal heads to be always shown and labeled. To do this, choose View, Network Elements from the menu in vSIM. In the resulting dialog box, check Signal Heads and label them by the signal group they refer to. Select OK to finish configuring. To create a detector, select the detector icon from the toolbar. The detector icon is the one with the square and a parallelogram sign. Let's begin by placing the detector for the northbound approach. To define a detector, left-click to choose the northbound link and then right-click upstream of the signal head where the detector starts. In the resulting dialog box, we will specify the following detector properties. For every detector, you will need to specify the number that was used in the signal timing plan. In our signal timing plan, we use detector number 6 to call the signal group 6. So number this detector as 6. Since detectors are defined by lane, more than one detector may be required at a signalized intersection. In addition, in the real world, there may be detectors that span multiple lanes. To model this, vSim allows multiple detectors with the same identifying number. So if you have more than one detector for a multi-lane traffic movement, you can simply define multiple detectors with the same identifying number. Next, we need to define a detector length, which is equivalent to the length of the detection zone in real-world detectors. In our case, we will use 25 feet as the detector length for all of our detectors. Next, we associate this detector with the free-running signal controller we just defined by choosing SC1 from the signal controller drop-down menu. In the detector type field, there are 4 options available. For our example, we will use the standard detector type. In the Position and Activation tab, the lane number, position of the detector relative to the stop line, and captured vehicle classes can also be defined. The Before Stop field defines the distance of the start of the detector to stop line of the signal head on the same link. The detector and the signal head must be on the same link for this option to be available. Let's define the Before Stop distance as 25 feet so that the detector ends exactly at the stop line. In the Vehicles Classes list box, we can choose the vehicle classes that are captured by this detector. You can select to choose more than one vehicle class by using the Control button while choosing. The PT Lines list box is only relevant when public transit lines are defined in vSim. Similarly, information defined in the Departure Signal tab is only needed when public transit lines are present. In the other tab, you can define the smoothing factors that affect how occupancy rates are computed every time step. Generally, these parameters do not require any changes. You can also choose to disable visibility of the detector and its label when using Show Network Elements functionality in vSim. In addition, you can optionally choose to play a WAV sound file when a vehicle is detected. The sound file should be stored in the same directory as the INP file. Select OK to finish defining the detector. We repeat the procedure to define the detector for the second lane. The detector can be moved by left-clicking and dragging the detector. To delete the detector, left-click on the detector and press the Delete key. Or alternatively, you can select and drag the detector off the link to delete it. Let's follow similar steps to define the detectors for the westbound and eastbound traffic movements. Number the detectors 4 and 8 respectively as defined in the signal timing plan. Defining pedestrian detectors is similar to vehicle detectors, except that they are smaller in length. To define a pedestrian signal for the eastbound pedestrian crosswalk, select the eastbound pedestrian link and right-click to place the detector upstream of the signal head. Number this detector as 108 and associate it with signal controller 1. In the length field, enter 4 feet and also enter 4 feet for Before Stop distance. We can associate this detector with the pedestrian vehicle class from the list. Click OK to confirm. The following steps can be repeated to define pedestrian detectors for the rest of the pedestrian crosswalks. Similar to other network elements, you can access the list of detectors by right-clicking outside the network. The list shows the signal controller number followed by detector number. You can access the data by selecting the detector from the list and selecting data. You can also choose to zoom into or delete a detector using this dialog box. It is important to remember that if you delete a signal controller, all the signal heads, detectors, stop signs, and priority rules related to this detector are deleted as well. In addition, if you choose to move or delete a signal group column in the RBC controller, all of the related network elements associated with the signal group are deleted as well. However, if you just renumber an existing signal group number in a column in RBC, all the references of related network elements are reset to the new signal group number. Before we view the signal in operation, let's configure the signal timing table to show us details about signal operation during simulation. We have already learned how to configure the table in a previous lesson. This time we will also add detector state to the table. The signal times table configuration can be accessed using the Signal Control Edit Controllers Signal Times Table Configuration tab. First, choose Signal Display from the Type field and add all of the signal groups to the list. Finally, choose State Detector and add all detectors to the list. Click OK to confirm. Let's start the simulation to view the free-running actuated control in operation. We can view the signal timing by selecting the Evaluation, Windows, Signal Times table from the menu and selecting Signal Controller 1 from the list. Since this is a free-running signal timing plan, and there is no cycle length defined, only zeros will appear within the timing window. The detector states are shown in blue. A light blue color represents the actuation was less than a time step long, while a dark blue color indicates the actuation was at least 1 step long. It is difficult to test the signal controller by watching the simulation. We will need to use the test feature in vSim to test if our signal controller is operating in free-running mode. The test feature in vSim allows the user to check their signal timing plan by manually placing detector actuations. To run a model in test mode, choose Test, Continuous from the menu. We can pause the simulation by switching to a single-step mode. To see how the detector actuations affect our signal timing, let's display the signal times table for the signal controller using the Evaluations Signal Times table. You will see that the signal controller starts up on signal groups 4 and 8 and rests in signal group 6 since there are no other calls. Left-clicking on the detector changes the detector state from no actuation, black, to single actuation, blue. Right-clicking places as well as terminates a continuous actuation, purple, on the detector. You will see that placing a continuous actuation on detector 4 brings up both signal groups 4 and 8 because they were flagged for dual entry, and placing a continuous actuation on all detectors will make the signal groups time their allotted split lengths. You can calculate the amount of time between two events by switching to a single step mode and left-clicking and dragging in the signal times table. The amount of time between start and end of the drag is shown in the bottom left corner of the window. Now, if you remove the call on detector 6 after it times its minimum green, the signal group will gap out after the extension time of 4 seconds.